Your laptop is powerful, right? It can run games, edit videos, browse 1,000 tabs, do basically anything you throw at it. But there is a specific type of problem that your laptop, every supercomputer on the planet, every computer that has ever existed, cannot solve in any reasonable amount of time. And we are not talking about it being slow, we are talking about it being so mathematically impossible that if you started calculating today, the universe would end before you got the answer. And quantum computers are being built specifically to crack those problems. And when they do, they will break the encryption protecting your bank account, your messages, your entire digital life, and simultaneously unlock discoveries in medicine, chemistry, and materials science that could save millions of lives. And the reason they can do any of this comes down to one of the strangest ideas in all of physics, the idea that a thing can be in two states at the same time until you look at it. So let us start with how normal computers work. Because once you understand that, the quantum version will make much more sense. Your laptop runs on bits, and a bit is the simplest possible unit of information. It is either a zero or a one, off or on, like a light switch. And everything your computer does, every video, every game, every email, is ultimately just billions of these tiny switches flipping on and off incredibly fast, and classical computers are extraordinary at this. Modern chips can flip billions of switches per second. But here is the fundamental limitation. At any given moment, each bit can only be 0 or 1, never both. And for most problems, that is completely fine. But for certain types of problems, specifically problems where you need to search through an enormous number of possible combinations to find the right answer, being locked into one state at a time is a crippling disadvantage. Like trying to find your lost keys by checking every drawer in the house one at a time when you need to check all of them simultaneously. Quantum computers replace bits with something called qubits, and a qubit is a bit that has been given quantum mechanical superpowers. And the first superpower is called superposition, which sounds complicated, but the basic idea is actually simple. A qubit can be 0, it can be 1. Or it can be both 0 and 1 at the same time, existing in a blend of both states simultaneously. And this is not a metaphor or an approximation, it is a literal physical reality. The qubit is genuinely in both states at once. And the way to think about it is like a coin spinning in the air. While it is spinning, it is neither heads nor tails, it is both, and only when it lands and you look at it does it commit to one or the other. And a qubit works the same way. It exists in superposition until you measure it, and the act of measuring forces it to pick a side. Now here is where it starts getting interesting. If one qubit can be 0 and 1 simultaneously, two qubits can represent four states simultaneously, 0, 0, 0, 1, 1, 0, and 1, 1, all at the same time, and three qubits can represent 8 states simultaneously. And this scales exponentially, which is a word people use loosely, but here it is completely literal. Because 10 qubits can represent over 1,000 states simultaneously, 50 qubits can represent over a quadrillion states simultaneously, and 300 qubits can represent more states simultaneously than there are atoms in the observable universe. And this is why quantum computers are not just a little bit faster than classical computers for certain problems. They are categorically different. They are not running faster on the same road. They are on an entirely different road that does not exist in classical physics. But superposition alone is not enough. If you just measured a quantum computer in superposition, it would collapse to a random answer, which is useless. And this is where the second quantum superpower comes in, called interference, which is the ability to manipulate the qubits so that wrong answers cancel each other out and right answers reinforce each other, like noise-canceling headphones, but for calculations. And quantum algorithms are essentially carefully designed interference patterns that guide the system toward the correct answer by making all the wrong paths interfere destructively and the right path interfere constructively. And designing these algorithms is genuinely one of the hardest and most creative problems in computer science. There are only a handful of quantum algorithms that have been discovered so far, and each one is considered a major intellectual achievement. The third quantum superpower is the strangest one, and it is called entanglement. And entanglement is what Einstein called spooky action at a distance. And it happens when two qubits become linked in such a way that the state of one instantly determines the state of the other, no matter how far apart they are. So if you measure one, and it collapses to 0, the other one instantly collapses to 1. Not because a signal traveled between them, but because their states are fundamentally correlated at a quantum level. And entanglement allows quantum computers to process relationships between qubits in ways that have no classical equivalent. It essentially allows the computer to work on connections and correlations between pieces of information simultaneously rather than sequentially. And it is one of the main reasons quantum computers can solve certain problems exponentially faster than anything classical. Now let us talk about what problems quantum computers actually break. And the biggest one, the one that keeps cybersecurity experts up at night, is called RSA encryption, which is the system that protects basically everything on the internet, right now your bank, your email, your messages. And RSA encryption works because of a mathematical fact that is easy to state. Multiplying two large prime numbers together is incredibly easy, but taking a large number and figuring out which two primes were multiplied to make it is incredibly hard. So hard that even the fastest classical supercomputers would take longer than the age of the universe to crack a properly encrypted RSA key. And this mathematical hardness is the entire foundation of internet security. And then in 1994, a mathematician named Peter Shor invented a quantum algorithm, now called Shor's algorithm, that can find the prime factors of a large number exponentially faster than any classical method. And a sufficiently powerful quantum computer running Shor's algorithm could crack RSA encryption in hours or days. And this is not theoretical, this is mathematically proven. The only question is when quantum computers get powerful enough to do it. And the answer is probably not tomorrow, but probably within 10 to 20 years. And governments and companies know this, which is why there is a massive race right now to develop post-quantum cryptography, new encryption methods that even quantum computers cannot break. And the US National Institute of Standards and Technology has already standardized several of these new algorithms in 2024. So the world is actively preparing, even if most people have no idea this race is happening. But quantum computers are not just a threat. They are also the most powerful discovery tool we have ever built for simulating nature, because here is a problem that sounds simple, but is completely unsolvable with classical computers. If you want to simulate how a molecule behaves, how its electrons interact, how it folds, how it reacts, you need to calculate quantum mechanical interactions between all the particles, and those interactions are exponentially complex. So complex that simulating even a relatively small molecule like caffeine at full quantum accuracy requires more computing power than any classical computer can ever provide. And this means we have been designing drugs and materials for decades using rough approximations and educated guesses, because we literally cannot compute the real answer. But a quantum computer does not have to simulate quantum mechanics because it is quantum mechanics. It naturally represents the same kind of superpositions and entanglements that molecules use, so simulating a molecule on a quantum computer is natural and efficient in a way it can never be classically. And this means quantum computers could let us design new drugs by accurately modeling how they interact with proteins, develop room temperature superconductors, which would revolutionize energy transmission design, better batteries, create new catalysts for pulling carbon out of the atmosphere, and solve problems in chemistry and materials science that have been completely locked to us because of the computational wall we hit every time we try to model quantum systems classically. So where are we right now with actual quantum computers? And this is where it is important to be honest, because there is a lot of hype, and the reality is that we are in what researchers call the noisy intermediate scale quantum era, or NISQ for short. Which basically means we have quantum computers that exist and work. Companies like IBM, Google, and a startup called IonQ are building machines with hundreds of qubits. Google famously claimed quantum supremacy in 2019 when their 53-qubit processor called Sycamore completed a specific calculation in 200 seconds that they claimed would take a classical supercomputer 10 years, and IBM disputed those numbers, but even accounting for the debate, the point stands that quantum hardware is advancing rapidly. The problem is that today's qubits are extremely fragile. They need to be cooled to temperatures colder than outer space. They are disrupted by the tiniest vibrations, electromagnetic noise, even cosmic rays. And this fragility means they make errors constantly. And the big unsolved engineering challenge right now is building fault-tolerant quantum computers that can detect and correct errors fast enough to run long computations reliably. And the current best estimate from most experts is that fault-tolerant quantum computers powerful enough to run Shor's algorithm on real encryption keys are probably 10 to 20 years away, though progress has a history of surprising people. The honest summary is this: quantum computers are not going to replace your laptop. They are not better at watching YouTube or running Word documents. They are a completely different kind of tool built for a completely different class of problems. And for those specific problems, they are not just faster, but categorically fundamentally more powerful than anything we have ever built. And the problems they are going to solve, breaking encryption, simulating molecules, optimizing complex systems, are some of the most consequential problems in human history. And we are building the machines that will solve them right now in labs around the world, inside refrigerators colder than space. And the decade we are living in right now will probably be looked back on as the moment quantum computing stopped being a science fiction concept and started being the technology that changed everything.